Today we're going to talk about VSePR, which is short for valence shell electron pair repulsion, or kind of the fancy way of saying molecular shapes. So what we're talking about when we talk about valence shell electron pair repulsion is when you have a covalent compound and you've drawn its Lewis structure, which we worked on doing in the last lecture, you should be able to see that these atoms naturally want to kind of space themselves apart. And the reason that they're spaced as they are is because the electrons repulse each other. So the electrons on one atom push apart and repel the electrons that are on another atom. And the idea is that they form a certain shape based on how many electron pairs you have. And that's why it's called the valence shell electron pair repulsion, because you're looking at how the electron pairs within the valence shells of all the different atoms within a Lewis structure, how they repel each other. So for our first one, we want to look at a couple different examples. So with this one, there's a couple things to look at. So I think I really like using this graph, and this handout is also on D2L if you want to go print it out and just follow along. But just kind of to start out with, what you see here is you see in black the black dot on each one of these shapes. So what you're looking at is all of these shapes, they have a black atom, which is your central atom. And then you have gray dots, which represent atoms that are bound to the central atom. And then the last thing that's possible is what you see here, and these two dots here represent an electron pair. Now the main thing to consider is that each line can be a single bond, a double bond, a triple bond, it doesn't matter. What matters is that it is somehow bonded to that central atom. So for our first shape, we have one central atom and two atoms bounded to it. They could both be double bonds, they could both be single bonds, one could be a triple, one could be a single. It doesn't matter. What matters is that you have a central atom and two atoms bonded to it. Within that, anytime you have one central atom with no electron pairs around it, okay, because if it did have an electron pair around it, it would look more like this bottom shape. But if you simply have one central pair connected to two other atoms, then it's going to always be linear. And that is both the molecular geometry and the electronic geometry. So what's going on here is the electronic geometry really kind of gives you the overall look of the structure. So it takes into play the placement of all the atoms. Whereas molecular geometry, it's what you get when you only look at the atoms and you're not looking at the electrons. We'll look more into that as we go along. So with linear, it looks linear. That's why it's called linear. It forms a line. If you go from one atom to the central atom to the other atom, it forms a line. Whereas the next two have the same electronic geometry of trigonal planar. It's called trigonal planar because it looks like a triangle and it's all in the same plane. So if you hold up a piece of paper and you draw a triangle on it, that would be how the atoms would line up. And the idea here is you can either have a central atom bound to three other atoms, or you can have a central atom bound to two atoms and an electron pair. It can't be one atom and two pairs, because then it wouldn't be a central atom. A central atom needs to be bound at least to two other elements, two other atoms. Okay, so these are your possibilities. So for a trigonal planar, you're going to always have 120 degrees be that bonding angle. For linear, it was 180 degrees. And the idea is if with linear you're in a plane, with trigonal planar you're in a plane. So those atoms that are not the central atom want to be as far apart from each other as they possibly can. So for linear, they're 180 degrees apart. For trigonal planar, they're 120 degrees apart. Why? 360 degrees divided by 2 gives you 180 degrees. And that's where we get our linear 180 degree bond angle from. Whereas 360 degrees divided by 3 gives us 120, which was where we get our bond angle for our trigonal planar from. Okay, so if we look at trigonal planar in a little more detail. The electronic geometry is, like I said before, trigonal planar because it looks like a triangle and it's in a plane. So that's why the first group within trigonal planar gives it the same name, and it's the same way for every different type we're going to look at. The very first molecular geometry category has the same name of the electronic geometry. Okay, so now bent. Where does the name bent come from? Well, if we ignore the electrons and just look at our atoms, it looks bent. Okay, and that's where the molecular geometry comes from, is what does the shape of the molecule look like if you cover up the electrons and just looked at the way the atoms were bonding. Okay, and so that's where the word bent comes from, is because the atoms, just looking at the atoms, it looks bent. So basically what's going on here is in order to figure out the electronic geometry and the molecular geometry of a compound, you first have to determine the Lewis structure. After you've done that, then you have to look and find the central atom, then figure out how many entities surround the central atom. So if two entities surround the central atom, there's only one option, linear. So what do I mean by an entity? An entity can either be a bonding pair or a non-bonding pair. So this would be your free electrons. Okay, and so notice there's no free electrons there, and a bonding pair, what do they mean by that, is atoms. Okay, and notice once again that bond can be triple, single, double. So with linear you have 1, 2 bonding pairs for a total of 2 things that are attached to the central atom. For trigonal planar, you have 3 atoms attached to the central atom, to the central pair. Once again, no free electrons, for a total of 3 things attached to that central atom. For bent molecular geometry, you have 3 things attached to the central atom, but 2 of them are atoms, and 1 of them is an electron pair. Okay, let's look at some pictures of these in kind of a 3D, see what they look like. So here is shown kind of the 3D view of it. This is called ball and stick model. The idea here is, once again, that this represents your bonds. They can be double, triple, single, and each of the balls that are involved in the ball and stick model represent atoms. And here is that trigonal planar structure shown with the 120-degree angles. These will be more helpful when we get to some of the more complex models. Alright, so now we're going to look at all of the structures that have a tetrahedral electronic geometry. Okay. So if you look at it, it's tetrahedral because if you try and picture that in space, there's a 109.5 degree bond angle between each and every single bonding pair. So within this, tetra means 4, and yet it looks hedral. Okay, so the idea here is if you try to draw, you kind of form like a triangle, it's going to not be planar anymore. Okay, it's going to very much be 3D with all of the angles being 109.5. My artistic drawing skills are not the best. Okay, but the key here is that there are 4 groups attached to every single central atom. It's just a question of, are each of the 4 groups all atoms? So we have all of these are all 4 atoms attached to the central molecule. The next one has 3 atoms attached to the central molecule and 1 lone pair. And then the next subcategory has 2 atoms attached to the central atom and 2 lone pairs. Okay. So then, because of that, each one of these subcategories gets a different molecular geometry. Now, once again, remember that the molecular geometry of the first subcategory is the same as the electronic geometry. So they have the same structure, because you're not removing any electron pairs. But if we look at the second one, so this trigonal pyramidal, if we were to draw the central atom, with each of the 3 atoms coming off of it, the electrons up here still initiate the 109.5 bonding angle, but if you look for the molecular geometry, it's gonna look like a pyramid of sorts. Okay, more of a triangular pyramid. It's not a square on the bottom, it's a triangle on the bottom, and that's really hard to see that drawing. Okay, but it looks more like a triangular pyramid, which is where the naming for this comes from. Trigonal pyramid. And then for the last one, it's called bent because you have one central atom with two coming off of it. Okay, and so it looks bent. It's not linear, but it's bent. So these two atoms will actually, you can connect all three of them in one plane if you want to. They are all bent. So let's look at some of the pictures for this. So here we've got CH4. So CH4, the Lewis structure, is drawn like this, but the way that it looks like CH4 is drawn, it looks like it's a planar atom. I mean a planar molecule. But it's not. It's very much not. It's 3D. And so what you're seeing here on the right-hand side is the depiction of each of the atoms in space. The idea that each hydrogen atom repels the other hydrogen atoms to get it to form this tetrahedral shape. Okay, here's another form of drawing. So instead of it being a ball and stick model, it's just a ball model. Okay, here's an example of our second subcategory of tetrahedral. So notice we have one central atom, three surrounding atoms, and one electron pair. So this is what this one looks like in space. So notice triangular pyramidal is its molecular geometry. Same tetrahedral shape if you involve the lone pairs, but the molecular geometry, it's more of a triangular pyramid. And so that's how it gets that trigonal pyramidal structure. Okay, and last but not least is water. So if you draw the Lewis structure for water, it looks like this. But truthfully, the better way of drawing it is like this, because that kind of shows the audience that you understand that it's bent. The idea is that these two water molecules, those two free electron pairs, they're going to be opposite of the two hydrogens, and so it makes it be a very bent structure, and so that's how it gets a bent structure for water. So if you were to ever ask the question, is water bent? Very much so. I know, you get that question often in everyday life. Alright, so here's the next category, trigonal bipyramidal. And what happens is you end up with almost this like T-shaped, which is what you can kind of see right here. So it kind of forms what looks like two pyramids. So you've got a T shape for one, but then these two that are coming off of the T help it form almost two pyramids in shape. So you have 120 degrees between some of the bonding angles and 90 degrees amongst the T. Okay. So, once again, the first one has the same category as the electronic geometry. They all will have 5 entities surrounding the central atom. It's just a question of, are those 5 atoms? 2, 3, 4, 5? Or is it 4 atoms and 1 electron pair? Or is it 3 atoms and 2 electron pairs? Or is it 2 atoms and 3 electron pairs? Okay, and each one of these helps give it its molecular geometry name. So seesaw, I think it looks like a seesaw, because if you kind of darken that in and then kind of draw the seesaw and then kind of picture 2 little kids playing on here, it looks like a seesaw if you look at it from the side. And T-shape gets its name because it looks like a T, and linear gets its name because it looks like a line if you just connect the atoms. Okay, so that's how, if you have an electronic geometry of trigonal bipyramidal, you're going to have molecular geometries of trigonal bipyramidal, seesaw, T-shaped, or linear. It all just depends on how many electron pairs you have, 1, 2, or 3. The last category is octahedral. So with octahedral, and most of our Lewis structures will not be octahedral. They'll have a total of like 4 atoms surrounding the central atom. But there are some that will fall into the octahedral category. So once again, octahedral is the first subcategory. you have 6 entities surrounding the central atom, and we're only going to look at the first 3 of this category. So you have 6 entities. In the first example, you have 1 lone pair, and in the second example, you have 2 lone pairs. So a square pyramidal, it looks like a square, but there's a pyramid on top of it. And then square planar, it's square planar because it's a square and it's all in one plane. Whereas octahedral, you basically have, it's kind of octopus-like, you've got almost like 2 pyramids, one on top of each other. And that's octahedral, to give you a total of 4 planes, basically. You have 4 triangles on each side, give you a total of 8 triangles formed. So 2 square pyramids. Okay? So whereas here you've got square pyramidal and square planar. So the idea behind using VSePR is that once you have figured out the Lewis structure for your molecule, you can figure out what the electronic shape is of your molecule. Let's do some examples. So for instance, let's say you're asked to find the VSePR shapes of hydrogen, sulfur, fluoride. The very first thing you have to do is draw the Lewis structure. So H, S, and F, which one is the least electronegative? Well, fluorine is the most electronegative out of all of the elements, so you know it cannot be fluorine. Hydrogen's never in the middle. So we've got hydrogen bonded to sulfur, bonded to fluorine. So hydrogen has 1 electron to donate, and there is 1 atom. Sulfur has 5 electrons to donate. Or no, sorry, it's right below oxygen. So it has 6 electrons to donate, and there's 1 atom of those. And then fluorine has 7 electrons to donate, and there's 1 atom of these. So 7 plus 7 gives us 14 electrons total on the element. So let's go ahead and fill in all the octets. And then we need to count and make sure it adds up to 14. So 8, 9, 10, 11, 12, 13, 14. 14 electrons, check. Fluorine has a satisfied octet, sulfur has a satisfied octet, and hydrogen has 2, so it's happy. Alright, so if I were to draw this in the ball and stick model, I would represent sulfur by this big ball right here. It's then bound to hydrogen, so I'll give it a little ball. And it's bound to fluorine, give that a little ball. Now, sulfur also has 2 electron pairs coming off of it. So I'm going to put those in little balls as well. So if we were to represent the central atom of hydrogen, sulfur, fluoride, this is what it would look like. So in determining VSePR, we have to look at the graph that shows a central atom connected to 4 entities. So we know its electronic geometry has to be tetrahedral because that is our only option for a central atom that has 4 entities around it. So electronic geometry is tetrahedral. Molecular geometry now. It has, does it have 4 atoms coming off of it? No, it has 2 atoms, 1, 2, and 2 electron pairs. So we need one with 2 atoms and 2 electron pairs. So our molecular geometry is bent. So hydrogen, sulfur, fluoride is tetrahedral and bent. Okay, the phosphate ion. Let's draw the Lewis structure for this. Which is least electronegative, phosphorus or oxygen? Phosphorus. And the whole thing should have a 3- charge. Alright, so let's see how this looks. We have phosphorus, 1 atom, times, if we go look at our periodic table, Phosphorus should have 5 electrons. Oxygen, 4 atoms. And it should have a total of 6 electrons to donate. Then extra electrons. Do we have any extra? We do. Why do we? We have a 3 negative charge. So we have a total of 3 extra electrons. So we have 5 electrons. 6 times 4 is 24, plus 3 gives us a total of 27, plus 5, 32 electrons total. So if we just simply add 8 electrons around every oxygen, sorry, 6 more, we already have 2, that's going to give us our Lewis structure for phosphate. So if I were to do a ball and stick model for phosphate, I would do one central atom bonded to 4 other atoms. So in naming this, what is it? 4 atoms surrounding the central atom. Tetrahedral, tetrahedral. Okay, what about hydrogen cyanide? So we have carbon or nitrogen. Which one is least electronegative? Carbon. So it goes in the middle. Hydrogen, 1 electron, 1 atom. Carbon is 4 electrons, 1 atom. And nitrogen is 5 electrons, 1 atom. No extra electrons because it doesn't have a charge. So 10 electrons to designate to everything. So if I just start adding electrons, 1, 2, 3, 4, I've drawn 8 so far, 9, 10. Okay, that did not work. Since it did not work, I know I need to make extra bonds. So let me switch over to my eraser, which is not going to let me do for a sec. Let me erase some of my electrons, and let me add some more. So what if I make it a double bond? How many electrons do I have now? 8 around carbon, 9, 10 total. Okay. But how many do I have around nitrogen? Nitrogen's still not happy. Why is nitrogen not happy? Because it only has 6. If you go and you look right here, 1, 2, 3, 4, 5, 6. Whereas carbon has 8. So carbon's happy, but nitrogen is not happy. So while I have 10 total, I still haven't made this completely happy. So let's erase that again, and let's try a triple bond. Carbon's happy because it has 8. Nitrogen's not happy because it has 8. And if we count all the electrons on this molecule, we have 10 electrons total. So we did a good job. So 10 total. Now I'm going to represent carbon by a middle central atom. It's connected to nitrogen, and it's also connected to hydrogen. Are there any electron pairs anywhere on it? No. So all we have here is one central atom bound to 2 separate entities, where they're both atoms. So what's that called? Linear, linear. Okay, because you have a central atom bound to 2 other atoms. So we've got to be linear, linear. Last example, dihydrogen monosulfide. Sulfur has to go in the middle because hydrogen never goes in the middle. Hydrogen, we have 2 atoms times 1 electron from each one. Sulfur, we have 1 atom, 6 electrons each. Total of 8 electrons. So this must be the structure for dihydrogen monosulfide. Alright, so if I had to draw this out, we have sulfur here in the middle. Then we're attaching it to a hydrogen atom, and then we have 2 lone pairs coming off of it. So what's that called? We know we have 4 entities, 1, 2, 3, 4. So these are the 4 that we have to choose from. So our electronic geometry must be tetrahedral. But does it have no electron pairs, 1 electron pair, or 2 electron pairs? It has 2. 1, 2. So that means its molecular geometry must be bent. Okay, so just kind of to recap, the first thing you always want to do is you want to draw the Lewis structure. You cannot figure out any geometries without the Lewis structure. You can guess, but it helps if you know the Lewis structure, because you won't always be right. Then you want to count the number of entities that surround the central atom. That will help narrow it down and help you figure out your electron geometry, because your electron geometry includes your electrons. Then you can figure out your molecular geometry, because though molecular geometry will ignore your electron, it still takes into account their effect, meaning their separation. But if you just look at the shape of atom bound to a central atom bound to an atom, that gives you your molecular geometry. So drawing Lewis structure can help you figure out how atoms are oriented in space within a molecule. And part of extra credit for this unit, actually not extra credit, I think it was just, yeah, it was just an assignment, excuse me. Part of your assignment for this unit is to make molecules. You can make them out of whatever you want. So kind of examples that students have done in the past is they've connected gumdrops with toothpicks and kind of tried to orient them in the right orientation. You've connected water balloons. You can connect pretty much anything. If you have humans that you want to connect in a shape, perfect. Whatever you want to do, just you have to take pictures of it for this assignment and post them in the discussion section. And just kind of to help you see that you can organize atoms. They're not just planar, they take on all kinds of fun three-dimensional shapes.